In section 10.1, we're going to be talking about correlation. So the key concept is introducing linear correlation coefficient R, which is a number that measures how well paired sample data fit a straight line pattern when graphed. So we're going to use the sample of paired data. Sometimes it's called bivariate data to find R, and then we're going to use R to decide whether there is a linear correlation between the two variables. So we consider only linear relationships, which means that when we graph them on a scatter plot, which we will with our calculators, the points approximate a straight line. We're going to discuss methods for conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for the two variables. So let's start just by considering this data here. And if you want, go ahead and pause and I'll make this a little bit bigger. You can pause and enter this data into your L1 and L2. We're going to be using it later, and it is quite cumbersome data. So again, you can pause and enter this into L1 and L2. But what this is saying is that there's chocolate consumption and Nobel laureates. So the amount of chocolate consumption and the amount of Nobel laureates from a specific country. So when we graph this in a scatter plot, it kind of looks like it's correlated, right? Like we could kind of draw a straight line. It looks like at the very least, it's increasing, right? So we could say like, if a country increases chocolate consumption, is it likely to experience an increase in the rate of Nobel laureates? And so, I mean, that's kind of what we're going to be talking about in this section. We're not going to answer that right now, but just something to consider. So again, we'll be doing correlation, linear correlation coefficient R. We're going to interpret scatter plots and then do some formal hypothesis testing. So correlation exists between two variables when the values of one variable are somehow associated with the values of the other. It's really important, correlation versus causation. Just because something is correlated, they both increase, they both decrease. One increases and the other decreases. That there's some sort of association doesn't mean that one causes the other. But linear correlation exists when there's a correlation in the plotted points of the paired data in a pattern that could be approximated by a straight line. And that's really what we're going to be talking about. So let's look at these four scatter plots. We can kind of see when we look at these four scatter plots that, okay, this data here looks like, and just a reminder, when we're reading graphs, we always read just like we read words from left to right. So we're always starting on the left. All right, so this looks like the data kind of could go like that. It's increasing. And again, we always start on the left. So this looks like the data is going down. And honestly, I could actually do better and show kind of through that point there. If I tried to draw a line here, I mean, I just really couldn't. This data doesn't really look like a line at all. Now, this data definitely has a pattern, but it's not linear. So even just looking at scatter plots, we can kind of make some assumptions here. So when we interpret scatter plots, it's kind of nice to have a value to say, like, if I see this value, this means it's linear. If I see this value, it means that, you know, it's going up or it's positive. If I see this value, I can know that the line is going down or that it's negative. So we call that linear correlation coefficient R, and it measures the strength of the linear correlation. So we use that to measure the strength, and I guess that just repeated itself. So here are some properties about R before we actually use it. The value of R is always between -1 and 1. 1 is a perfect increasing line, and -1 is a perfect downward line. If all the values of either variable are converted to a different scale, the value of R doesn't change. So it's not like if we multiply everything by 10 or divide everything by 10, the value of R isn't going to change. It's not affected by the choice of X or Y. So we could interchange X and Y and R will still not change. And again, it measures the strength of the linear relationship. It is not designed to measure the strength of a relationship that is not linear. We kind of saw that with that quadratic shape. R is very sensitive to outliers in the sense that a single outlier could dramatically affect its value. We'll talk about that more in 10.2. So when we look back at these values that we already assessed earlier, we saw that this was a positive increasing line. And so the R is positive. and it's really close to 1. Remember, 1, excuse me, is a perfect line up, and -1 is a perfect line down. So this is a line going down, so we know that R is going to be negative. And see how much closer together those data points are? These are a little bit like further off, so that's why the R is a little bit less than this one here. That's more packed closer to a straight line. Here, it's almost 0, right? There's just no correlation. And then here, it's a nonlinear relationship. So there is some sort of relationship, but it's not linear, so it's like 0.3. So go ahead and give this one a try, matching these values over here with the scatter plots that you see, and then press play when you're ready to see the solution. And there you go, and there's some reasoning for you. So calculating and interpreting the linear correlation coefficient R. So there are some requirements, but we're going to assume that all the requirements are met for the data that we're working with today. And we actually use it in our calculator. So step 0 is always to enter the data into the list. And then once you do that, once you have the data in your list, you can press Stat, Test, Linear Regression T-Test, and then enter the list for X and Y. 1 for frequency. We'll talk about beta and rho. We're going to use not equal to 0. We're going to talk about Y for a moment, but in a moment. But the reason is that basically is saying we're testing it against no correlation, not equal. And then calculate. And then this right here is how we would graph the scatter plot. We'll go through it. And I know everyone likes to know about rounding. Round the linear correlation coefficient R to 3 decimal places. So once we have the R, and we want to interpret the linear correlation coefficient, we can compare it against our significance level. We'll get a p-value from the calculator, and if it's less than or equal to our significance correlation, no correlation. When we're using critical values from the spreadsheet, and I'll show you that in a moment, we'll use the absolute value of R compared with the critical value. If it's greater than or equal to the critical value, it's correlation, less than, no correlation. These are great things for a cheat sheet. Now, the Spreadsheet Calculator is a link, and it will be linked in Canvas as well, but it is a calculator already built into Excel. And basically what you're going to do is you'll just type in the sample size here. You might have to adjust this, and it'll automatically calculate the critical value of R for you. And we usually do two-tailed. Remember, that's not equal to, it's two-tailed. So let's find the value of the correlation coefficient R. So we're going to type this data into our calculator. Now, I already, I saved my chocolate Nobel laureate data, so I will go into Stat, Edit, and I'm going to put this into L3 and L4. Remember that if you lose anything, you can run the setup editor to get your L's back. So I'm going to type this in. I'm going to make chocolate my X, and remember, it actually doesn't matter. It will matter, you know, later, but for right now, just calculating R, it doesn't actually matter. Okay, so we're in L3, L4. We're going to go to Stat, Tests. We're doing Linear Regression T-Test, right? We're not doing an interval, we're doing a test. Our X list is actually, well, yours might be in L1 and L2, but mine is in L3 and L4. And we're going to almost always do not equal to 0, and we'll talk more about that shortly here. So when we do this, we get T is our test statistic, which we don't need right now. P is our p-value. A has to do with our line, which we don't have to do right now. B has to do with our line. All the way at the very bottom is our R, 0.795, because we're going to do, so R is equal to 0.795. And if you remember, that's probably going to be a straight line, and pretty close to a straight line increasing, pretty close to 1. If we wanted to see what that looks like, we could kind of go back here. So I'll pull this back up. So if we wanted to see what that, and that isn't what the question asked, but if you're just curious, we would go to second y equals to stat plot. We would turn stat plot on. If it's not already on, we would click the stat plot, scatter plot. And then mine are in L3. Yours might be in L1 and L2, L4. If you want circles, you could do circles, whatever you want. And then you're going to go to Zoom, Stat. You might want to click 9. And then there's our scatter plot. And it does kind of look like it's an increasing line. It's definitely not one. It's definitely not perfect. Those 3 points really look perfect, but those other ones are kind of steering it away. So again, you just have to calculate R here. So for your U try, just go ahead and calculate the coefficient R. You don't need to worry about graphing it. Press play when you're ready to see the solutions. And there you go. That's going to conclude part 1. When we come back for part 2, we'll do formal hypothesis testing.